Welcome to another video in the series about the C7000 compiler. This is the first of two videos which explain the most commonly used compiler options. My name is George Mock and I'm your guide. This video does not explain all of the options of the C7000 compiler. Instead, it explains the ones that are in these categories. In part 1, this video, we're talking about the compiler options related to getting good performance. In part 2, we'll talk about these other two categories of options that I'll explain at the beginning of that video. Before discussing performance options, there are some basic details to describe. All of the compiler options have a long form that begins with 2 dashes. Many of the compiler options, but not all of them, have an equivalent short form that begins with 1 dash. So here's some examples, and these will actually appear later in this video. So the long form of dash op level. On the command line you can write dash op level, or you can write -o. Okay, and so on for these other options. In this video, I always try to use the long form because it's more descriptive, and when you're first learning them, it makes it more clear as to what's going on. However, you might catch me when I'm just talking about options. I might use a short equivalent. I might say -o when the video shows dash op level. I hope you show some patience with me over this. Next, I'll show you some features of the compiler by demonstrating them from the command line. Now, I realize next to no one actually uses the C7000 compiler from the command line. But for demonstration purposes like this one, this works well, so please show some patience towards that. So the first thing I want to show is CL7X. I'm going to run it through more. If you run it with no options, what you see is this is a summary of the compiler options, like that. Okay. Go ahead and kill this off. Another feature I want to show you is CL7X. So notice the dash help there, and then debug. You're saying I want to search the options for anything related to debug, and you'll get this output right here. Okay, so it starts here. This is what I want you to focus on. And this is just all the options that either debug appears in the option name or somewhere in the description. And these are short descriptions right here. Necessarily, smaller in size than what appears in the manual. So if there's any question or confusion about what these means, go look them up in the compiler manual. Now the video focuses on compiler options related to performance. The most important of the performance options is dash op level. It takes an argument. And what these arguments mean to op level is, well, how much of the input program, the input file, should be considered at a single time in order to make optimization decisions. So off means none, pretty obvious. 0 means look at one statement at a time. So consider one statement, and a statement in C programming language is roughly those things that are separated by semicolons. Look at one statement, make some optimization decisions, forget about that statement, move on to the next one. Okay, and so on with blocks. A block is a group of statements surrounded by braces. Okay, function and file, those are pretty self-explanatory. And then op level 4 is between files and libraries. I will be talking about that in more detail here soon. Now this is just a rough summary of the differences between these different optimization levels. There is a more detail in the compiler manual on that. In particular, if you go look that up, you'll find that there are some level 0 and 1 optimizations that range a bit farther. Op level 3 is the most typical setting that we see when we work with customers. C7000 does depend on software pipelining of loops to achieve maximum performance. In fact, this is so important that we have multiple videos planned in this video series just on the topic of software pipelining. What's worth mentioning here is that software pipelining requires that you build with optimization level 2 or higher. Here are some details regarding opt level 4, also called link time optimization. It optimizes across the entire program. And what's happening is, as part of the link, additional optimization passes happen. It takes a bit longer, okay? Something to expect when you're doing this. But the upside is it presents opportunities rarely seen just within a single file, okay? For example, you might see all the calls to a function, and you might notice that, say, the second argument to the function is always the same. Say there's some function where the second argument is some length, and every time it's called, it's always passed the same number. Say it's 256, right? Well, under O4, opt level 4, the compiler can see this situation. It knows it's seeing all the calls to this function, and it's always 256 for that second argument, and it'll just replace it. It won't pass it anymore. It'll just replace it, and then inside that function, 256 replaces all those arguments, and then further optimization happens, and so on and so on. So this is the kind of thing that can be a big win for you with opt level 4. One detail to keep in mind is you have to use opt level 4 during the compile and the link. If you build with CCS, that detail is taken care of for you. If you're among the people who are configuring your makefile for your build, this is something you need to take care of. What's happening under the covers is that information encoded in object files during the compile is used by these additional optimization phases that happen during the link. Libraries built with opt level 4 can participate. Now, libraries that are not built with opt level 4, they're built with some lower level of optimization, don't, ruin the whole picture, but they are less than ideal. So among the things we are trying to do is to get yet more and more libraries to build with opt level 4 so that this optimization can be yet more effective over time. There's a trade-off to consider between debug and optimization. What am I talking about? Okay, the compiler emits debug information that is used by Code Composer Studio. That's how Code Composer Studio can know things like, well, where are the variables in memory and what line of source is executing right now, that sort of thing. It works that out because of the debug information that's in the object file that the compiler put there. You don't need -G to have this happen. Okay, the debug information is always emitted. That said, -G is still silently accepted by the compiler because it is just so commonplace among compilers everywhere that -G means debug. Let's get to the heart of the matter. Optimization affects the ease of debugging. What am I talking about? The higher the level of optimization that you have, the more likely it is that things like this will happen. Variables may be optimized away. If a variable is optimized away, it doesn't mean anything to try and inspect the value of that variable or set a watch on it or anything like that. I mean, it's gone, right? Operations may be performed in a different order than as it's written in the original source code, and that can become confusing, right? And again, the higher the level of optimization, the more likely it is these sorts of things are going to happen. So this is one of these things where you need to experiment and work out what level in the trade-off works best for you. Now coming up, I'm going to give you a couple of techniques you can use to try and keep your optimization level higher than otherwise, yet still debug a specific problem that might be happening. Suppose your situation is you build your project with CCS, Code Composer Studio. You're using a high level of optimization because you need to meet your performance goals. And there's some debug problem that is difficult to get at, but you have isolated it down to a single file. You know which file it is in the project that the problem is likely to be located. So what you can do in that case is you can reduce the optimization level not for the entire project, but just for that one file. And the way you do that is you right-click on the name of the file, and then you choose Show Build Settings, and then it's pretty obvious from there how you can change the optimization level just for that file. Here's another way to reduce optimization in a more localized way. In this case, it applies to just one function. So you're using a high level of optimization, you've got some problem you need to debug, you've isolated it down to a single function, and you want to try and reduce the optimization level just for that function. Well, here's how you can do it. You use this pragma called function options. The details are different between C code and C++ code. Okay, you can look at it here. You can freeze this this frame in the video and get a look at it, or go look it up in the compiler manual. Just go look up function options and see how it's different between C and C++. One note worth making: you have to build with some level of optimization for this to have that effect. If you build with no optimization at all, then this function options pragma gets ignored, and then the whole thing doesn't work the way you might expect. Here is another trade-off you need to consider, and this one is between speed or space. Now, most optimizations improve both speed and space. You know, it's a matter of you're removing an instruction, you don't have to execute it, and it's not taking up space in memory. That said, there are a few optimizations that improve one while degrading the other. And here's two examples. Loop unrolling is where you make multiple copies of the body of a loop and then reduce the loop count accordingly. And there are situations where that can lead to an overall speed up, but it takes more instructions to do that, or it takes more size to do that. Another example is function inlining. This is where instead of calling a function, you make a copy of the statements for the function and put them at the call site. All right, it obviously makes the code much bigger, but again, there are cases where that can be a real win with regard to overall performance, because once you take those statements from the function and put them at the call site, further optimization tends to happen when you do that. So you want a way to control this, right? And the way you do it is with an option called opt for speed is equal to value. The values can be between 0 and 5. If you don't specify opt for speed at all, you get opt for speed equals 4. Okay? So if space is a concern, if you're trying to save some space, you don't reduce opt level. What you do instead is you reduce your opt for speed. And this chart over here gives you a sense of how the trade-off works. At 0, the thing that the compiler will try to do for you with regard to these optimizations is it'll go for the smaller size. If you say 5, it's going to go for the fast speed without any regard for how much space it takes to do it. Okay, that sort of thing. Now, remember the techniques I already showed you about how you can lower opt level in a localized way in order to debug a particular problem? This is something you could do with regard to the option opt for speed. Something you might consider, you could have a fairly low setting for opt for speed for the whole project, but for a few files or maybe a few functions where you know speed is a big deal, change it to opt for speed equals 5. There is a way to have the compiler remove the functions that are never called in the program. And the way to do that is you build with an option called --gen func subsections. What that does is it puts each function into a separate subsection. And then when the link happens, the linker recognizes the ones that are never called and it removes them. Now, something to keep in mind is if only a few functions get removed, the overall code size may increase. All right, and this is because there are some minimum section alignment requirements. Every section, including all these different subsections that appear because you built with this option, every single one of those has to be aligned, and that can, cause a bit more memory to be used. And so if only a few functions get removed, this, using gen func subsections can, in some cases, cause an overall size increase. So it's something to watch for. The acronym SE stands for Streaming Engine, and SA stands for the Streaming Address Generator. These are hardware features of the C7000 DSP that further improve throughput from memory and loop performance. Okay, And there are some compiler options that are related to them and how the compiler will automatically use the SC and the SA. All of this is sufficiently complicated. You need to have an understanding of the SC and SA and so on, that it makes more sense to describe these options in the video about the SC and the SA that we already have planned. So look for that in that video. I will close this video with two references. The first one is to this web address, which is a lot to type in, so another way to do it is to do an internet search for C7000 compiler. With all these search engines I've tried, this web address is the first result that's returned. Regardless of how you get there, this is the home page for the C7000 compiler. It's where you can download it, access the manuals, and more details like that. The second reference is to e2e.ti.com. This is where you can ask any question about any TI product, including the C7000 compiler. If that question is related to the compiler, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.